Now let's continue with spatial coding in V1. Let's recall that spatial coding in V1 differs from that in the retina, and in particular in the third step of this efficient coding transform, the inverse Fourier transform is now replaced by this block diagonal matrix to achieve translation and scale invariance to some degree. As a result, the full spatial frequency range here is divided into multiple bands, one band for each submatrix. So each submatrix serves to multiplex the frequency components of visual input within a single frequency band. As a result, there are multiple scales of residual filters. Each scale corresponds to a single frequency band and a corresponding residual shape. Okay, in the low noise limit, different scales have the same residual shape, but the spatial size of the residuals are scaled versions of each other, and amplitude also are scaled. This is for a one-dimensional space. For a two-dimensional space, the frequency space is also two-dimensional. Okay, as illustrated by this Fourier spectrum for this image. The residual fields will also become two-dimensional. These are two examples. Yeah, and this is actually oriented, yes, horizontal orientation. And again, in different scales, they are the residual size change, or the shape doesn't change, and so they are scale versions of each other. And for this filter, for example, its frequency band will also be two-dimensional, no longer this one-dimensional range, but two-dimensional. For example, the frequency band can look like this one. Okay, it spans this horizontally and that vertically. And of course, to make this filter real, you have to also include the negative frequency. So it's a mirror image of that relative to this zero frequency. So therefore, this for this filter, it spans this low frequency range from here to there in a horizontal direction, but higher frequency range from here to there in the vertical frequency direction. And this can be seen from this filter shape because it varies more along the vertical direction. Therefore, for the vertical frequency component ky, but it varies less horizontally for the horizontal frequency component kx. In other words, the vertical frequency is higher than the horizontal frequency. So vertical is higher than the horizontal. Yeah. Or one can say that this is a band pass filter along this way, but more like a low pass filter along this way. Therefore, by having multi-scale coding, we achieve orientation selectivity of the residual fields. Now, if another band of frequency is selected, for example, this one, yeah, now the horizontal frequency is higher than the vertical frequency, horizontal, vertical, yeah, then you can imagine this will be the residual field shape. It will be oriented vertically. You can imagine that for this filter, it is smaller, so it should be tuned to higher frequencies. So its frequency band should be somewhere around here. And so therefore, carving up this two-dimensional frequency space by many different frequency bands, we can have residual field filters tuned to different orientations and different spatial scales. Carving up the frequency space with different frequency bands covering different frequency regions without any overlap, comes from this block diagonal unitary matrix as the multiplexing step in the efficient coding transform. It is designed such that different submatrices in here do not overlap in the columns or the rows of this matrix. And there are as many output neurons to represent or encode the visual inputs as the number of frequencies available or the number of sensory input pixels. So if V1 indeed does the visual encoding this way, then there will be only two orientations of the possible residual field shapes. However, V1 has an overcomplete representation. There are many more V1 neurons in monkeys and cats than the corresponding number of retinal ganglion cells. The frequency bands overlap with each other extensively, like this, schematically illustrated here. For this vertical filter, it's small, so tuned to higher frequency. The frequency band is here. Of course, also its mirror image here. So this is the horizontal frequency, this is the vertical frequency, yeah? For this horizontal filter, so it's tuned to this frequency range and its mirror image here. Now here's another horizontal filter. It's larger than that one, so must be tuned to a lower frequency, so around here and there. You also notice that in the middle, low frequency for the horizontal frequency and vertical frequency. This circle covers a special frequency range. They're really low frequency, and therefore it has a larger residual field, and it's not tuned to orientation. For the V1 neuron, tuned to this frequency band, and it's not orientation tuned. This filter will be perhaps tuned to a frequency range around here, while this filter, smaller than that and tuned to a different orientation, should be to a higher frequency range, perhaps somewhere around here. Each filter type involves many neurons whose residual fields tie up the whole visual space. Therefore, the smaller a filter is, more neurons will be involved. So for instance, compare this filter to that filter. They have the same shape, but this one's bigger, so fewer neurons are needed for this filter type than that filter type. You note that the frequency space here are linear, so therefore even though different bands, for instance this one and that one, they have the same bandwidth in terms of octaves, they cover different sizes in the linear space in frequency. That means this one should have more individual frequencies in this region than that one, and so therefore this one involves more neurons. If we look at the lowest band, this isotropic band, involving the largest residual fields, and because it has the smallest space in linear frequency space, then you will have fewer neurons to tie the whole visual field. That's okay because this residual field is bigger anyway. So therefore, if you look at each visual location in visual space, you will find many different neurons covering that location. So at each location you have this neuron type, that neuron type, and so on to cover it. And they are tuned to different orientations, different frequency bands, they have different sizes, and so on. Here is a one-dimensional profile of the spatial frequency tuning. The horizontal axis represents only the magnitude of this two-dimensional spatial frequency. So different filters cover different frequency bands like this. So for instance, here's the low frequency band, lowest one should represent this lowest one, and the next band should represent these ones, and the next band these ones, and so on. Note that frequency here is on the log scale, so therefore these different frequency bands, they have the same bandwidth here, while here the frequency is on a linear scale. So those bands tuned to higher frequencies also have higher bandwidth because the bandwidth scales with the average frequency in each band. This picture also on the vertical axis shows the gain of these filters. Gk is a function of k. We recall that this Gk comes from the second step in the efficient coding recipe. And it looks like we can inherit this Gk gain curve from the retina to the primary visual cortex. Although different filter bands have different gains through this Gk curve, the overall system should still have a contrast sensitivity function, contrast sensitivity curve. And this curve can be reflected in visual behavior of the whole animal, and one can measure it by visual psychophysics experiments, such as that in human observers, and this we have visualized ourselves previously. Overcompleteness is difficult to be understood by efficient coding alone. V1 has about 100 times as many neurons as retinal ganglion cells, and there's many different preferred frequencies and orientations of the neurons, and the orientation tuning curves and frequency tuning curves overlap extensively, and at each location there are many more neurons, and the reciprocal fields overlap much more extensively and more densely distributed than required for a complete tiling of the visual space. That makes the translation invariance and scale invariance much more flexible, because you don't have discrete jumps in spatial locations and discrete jumps in scales to make these translation and scale invariance. However, all these overcompleteness makes the representation very redundant. More neurons require a higher cost. So all these are very difficult to be understood purely by efficient coding principles. But let's ask whether the efficient coding principle can help us look at V1 coding in other feature dimensions such as color, time, and stereo. This we can do by looking at the coupling between spatial coding and other feature coding. To do this, we can just look at these spatial filters as they are with a model, and this we can model as a Gabor filter for each of these filters. Okay, this Gabor filter is a function of space x. It really is a cosine wave within a Gaussian envelope. So this is a cosine wave within a Gaussian envelope and has an amplitude A, and this amplitude A should scale with the gain G, and so G at the average spatial frequency K of this wave, and also this sigma gives the size of the Gaussian envelope, so it's a small size or bigger size and so on, and this size is inversely scaled with the frequency. So for filters tuned to higher frequency, you have a smaller size. And we also have the phase of the filter. So if the phase is 0, this is an even function of space x, like this one. But if the phase is 90 degrees, it will be an odd function of space x, like that one.